Hello, chemistry students. We're going to be talking about scientific notation in this video. So first of all, what is scientific notation? Well, scientific notation is a way of expressing a number as opposed to its decimal form, which would be our standard notation. Then scientific notation is a string of digits that has at most and exactly one number to the left of the decimal place. So for example, 2.35. And then it is multiplied by 10 to some power to indicate the actual position of the decimal place if we were to convert it back to decimal form. What do I mean by that? Well, this might be 2.35 times 10 to the 5th power, or 2.35 times 10 to the negative 7th power. In these instances, of course, this 10 to the 5th is going to indicate that this is a number that is much larger than 2.35. Okay? This, the negative 7th, is going to indicate that this is a number much smaller than 2.35. Now we're going to talk about converting between decimal and scientific notation, but before we get there, let's talk about the why. Scientific notation is useful when we're dealing with very, very large numbers or very, very small numbers, and we're going to run into both of those eventualities in our chemistry class as we get further on into the more complex calculations. So we need to be able to deal with scientific notation in order to wrestle with those very large or very small numbers. And scientific notation is also useful in indicating the number of significant figures that we're going to have in a particular digit or in a particular number. So how do we convert from scientific notation to its decimal form, or from decimal form to scientific notation? Well, we'll look at a couple of examples. We'll first deal with a large number. So for example, 39,500,000. Now this isn't a huge number to deal with. It's something that we're fairly used to dealing with, but it could still be made a little bit more compact. So let's put 39,500,000 into scientific notation. Scientific notation basically deals with moving the decimal point around. In this number, we understand that there is an understood decimal point right there. So to put this into scientific notation, we need a number that has exactly one digit to the left of the decimal place. The way we understand that is by shifting this decimal place 1, 2, 3, 4, 5, 6, 7 times, so that we have 3.95. And then that 3.95 is going to be multiplied by 10 to some power, and that power is indicated by not only how many places the decimal moved, but also the direction that it moved. In this case, we moved the decimal to the left. And since we moved it to the left 7 times, that's going to be a positive 7 exponent. Now we're going to talk about left and right in relation to individual problems. I would suggest that you not memorize the left or right movement, and instead understand it as a relationship between the two numbers, the number in its scientific notation form and the number in its decimal form. A leftward movement of the decimal place indicates a smaller number if we were to compare only the decimal forms. And of course, 3.95 is much smaller than 39.5 million. Since this number is much smaller than this, to indicate that, we are multiplying it by 10 to the 7th power to tell everyone, okay, we're dealing with this 3.95, but in reality, if we were to look at this number in its decimal form, that decimal place is going to be 7 places to the right. And of course, it can work the opposite direction if we had a negative exponent, but again, we'll get to that example in just a minute. So we have this 3.95 times 10 to the 7th. We have a nice compact form. We know at a glance exactly how many significant figures there are. In this, Of course, we understand from our rules that there are 3 significant figures, but it's a little bit ambiguous because we didn't know for sure if in the measurement maybe one or two of those zeros was significant. But in this situation, it's very clear. There are only 3 significant figures. And if we had a situation where we had a measurement like this, 3.950 times 10 to the 7th, well, each of these numbers in the value that they express is exactly the same. But this and this and this are different in the number of significant figures that they indicate. And so it's easier in a setting like this to indicate significant figures of a very large number when we're putting it into scientific notation. It's easy to see at a glance. Oh, exactly 4 significant figures. So when you're writing scientific notation, every digit that you write down in its decimal form is going to be significant. So we have this decimal form to scientific notation. What if we're going from scientific notation back to decimal form? Well, let's go ahead and cover that up and imagine that this was our starting place, 3.95 times 10 to the 7th. Well, again, what we're indicating here by this 10 to the 7th is we're indicating that this number is actually much larger, that decimal place is actually much further to the right than we express it here if we were to put this number in its decimal form. So we can take that and just imagine that we're going to be shifting that decimal place 1, 2, 3, 4, 5, 6, 7 places. So we're going to start writing that out. So we had the 3. The first shift of the decimal place is in the 9. That's 1. 5, that's 2, 0, that's 3, and we still have 4 more there. So 3, 4, 5, 6, 7. And we're going to put our commas in the appropriate places. So this is why I would suggest that you not memorize the left or right movement. Because when you're going from, with a large number, when you're going from decimal to scientific notation, the movement of the decimal is to the left. When you're going from scientific notation to decimal form, the movement of the decimal point is to the right. And so rather than memorize 4 different situations where you're having this decimal shifting around, again, think about the relationship. 3.950 as compared to 39,500,000, it's getting bigger. That 10 to the 7th, that's what that's doing. It's making this number larger, and we understand that that happens because the decimal shifts to the right. Okay, so that is dealing with a large number, going to scientific notation and back. What about a small number? Something that looks like this, 0.000000293. Well, in this case, again, what we want is we want this string of digits to be a part of our scientific notation, because we want all the digits that are significant, and we want exactly one of those to be to the left of the decimal place. So in this case, what we're going to have as our goal is 2.93. But then we have to decide, all right, when I've got this 10, what power am I going to raise that to? So again, what we're going to do is we're going to count the movement of that decimal point. We're going to see how many places it moved. In this case, it's 1, 2, 3, 4, 5, 6, 7. Probably should have chosen an example that had a different number than the last problem, but it is what it is. 7 places that decimal place is going to move. But again, when we think about the relationship, this number is much larger than this one. So these are not the same numbers right now. In fact, they're vastly different. So what we have to do is we have to indicate by the sign on our exponent which direction we need this decimal place to move if we are going to come up with this number in its decimal form. In this case, to make this number smaller, that decimal place needs to move to the left. And a leftward movement of the decimal point is accomplished by a negative exponent. So 2.93 times 10 to the negative 7th is the same as 0.000000293. So again, we can see this number is a little bit more compact, a little bit easier to deal with, less confusing, as long as we understand what it is that this 10 to the negative 7th is doing. Okay, so in this case, we had a movement of a decimal to the right. But what if, again, we were to go ahead and cover up that top portion and talk about converting from scientific notation back to decimal form? Well, in this case, that negative 7 indicates to me this number is going to get smaller, right? That's going to happen as this decimal place moves to the left. So I'm going to have to start out with something like this. 0. Well, how many zeros do I place? Well, I've got 7 spots that decimal is going to move, 7 positions. One of those is going to be taken up by the shift to get around this 2, and the other 6 are going to be taken up by the zeros that we're going to write down. 1, 2, 3, 4, 5, 6, 7 places. So again, when we're going with a very small number from decimal form to scientific notation, the decimal place is going to move to the right because we're dealing with a number that is larger in its decimal form. This 2.93 is larger than the 0.000000293. So that decimal is shifted to the right. But in order to keep this and this equivalent, we've got to multiply by a negative exponent. When we're going the other direction, we understand it as a shift of the decimal to the left. As this number is getting smaller. That 2.93 is shrinking, in a sense, down to 0.000000293. Now again, I am talking about this in relation to shrinking and growing larger as if the number were actually changing. It's not. This number and this number are exactly the same. They just have a little bit of a different look because of being multiplied by 10 to some power. So I hope that helps you out in your understanding of this. Again, think about it as a relationship. Think about it as a shifting of the decimal place. But understand that, talking about it to the left, to the right, probably not the best understanding of it. Think about it as how these numbers relate to one another. And use this to express how these two numbers are different from one another when it comes to the position of the decimal point. As always, if you have any questions, contact me, email me, send me a message, post on the video, and hope that helps you all out. Have a good day.